Welcome to the lecture series on process integration. With this lecture, I am starting a new module which is module number 4, and this is lecture 1, and this is on energy targeting procedure. As I have told you, we are going to see a new important feature of process integration. This feature is the ability to identify performance targets before the design step is started. What it means? That before designing the hen, I can find out the important parameters, or I can say the important target parameters for the design, which has to be achieved through the design step. This is a new feature of the process integration in the pinch technology or in pinch analysis. Targeting procedure also helps in the evaluation of alternative hen designs, because many designs or many competing designs which satisfies the constraints of pinch analysis can be developed. Now, which hen design should be accepted? Now, the targeting procedure tells us that I should select that design which meets the targets. Now, if we see the targeting procedures, there can be many targets which can be set before the design for a specified value of delta T minimum. Such targets are energy targets. In the energy targets, we find out the minimum energy consumption through external heating and cooling for a certain delta T minimum value. And when we change this delta T minimum value, this energy target also changes, because the delta T minimum value affects external heating and external cooling. The second target is fewest number of units. Pinch analysis also helps to find out before the design what will be the number of units in the heat exchanger network. These number of units include process heat exchangers, heaters and coolers. So, when we find out the number of units, it is a summation of process to process heat exchangers, heaters and coolers in the hen. In a third targeting procedure, we find out the fewest number of cells in the heat exchanger network. That means, it will tell that how many number of cells will be present in the total heat exchanger network. Why we have gone for this? Because the counting of units will not give me that accurate result about the number of units as the cells will be giving, because a heat exchanger can be made up of many cells in comparison to one cells, and this happens when we are dealing with low FT parameters. A heat exchanger with single cell and a heat exchanger with a multiple cell, if we compare the cost, the heat exchanger with a double cell, the cost will be almost double in comparison to single cell. So, the number of cells count or number of cells target will give me a better picture about the heat exchanger network. Obviously, if we have designed two heat exchanger networks hen 1 and hen 2 and hen 2 has got less number of cells than hen 1, one may select hen 2 because it has less number of cells. Then fourth is minimum total heat transfer area. The heat transfer area of a heat exchanger network gives a fairly accurate estimate of the cost of the heat exchanger network, and hence before the design it is always advisable to find out the minimum total heat transfer area as a target. The fifth target is cost targeting, through which we can use the heat transfer area target and we can use the energy target. So, heat transfer area target will provide the fixed cost component of the cost targeting, and energy target will give us the operating cost part of the cost targeting, and we can add these two targeting procedure to find out the cost targeting. So, we have seen that there are 5 number of targeting procedures are available with the bench analysis, and these are very important because before design they set the parameters for the design, and in the design in general we try to meet these parameters, and if we are not able to meet these parameters in the design, that means some fault has been carried out in the design or the design has moved to a different path than the path it should move. Results obtained from these targets lead the design in right direction and help to search for a optimum topology, because we have already seen that using the pinch analysis we can design a number of heat exchanger networks for a given problem. If it is so, then how to find out the optimum or the best heat exchanger network, and this targeting procedures help us or lead us or guide us to the optimum topology or optimum design of heat exchanger network. So, now it must be clear that what is the importance of a targeting procedure. Now, we will see the first targeting procedure, which is energy target, and we also know that the energy target can be achieved through the composite hot curves and composite cold curves. The energy targeting can be done through hot and cold composite curves, grand composite curves and problem table algorithms. So, there are 3 different methods which are available to you to do the energy targeting: hot and cold composite curves, then grand composite curves and problem table algorithm. Hot and cold composite curves are a graphical method. Grand composite curve is also a graphical method, which the grand composite curves are derived from hot and cold composite curves or can be derived from a problem table algorithm. And the problem table algorithm is a algebraic algorithm to find out what is the energy targeting. This algebraic algorithm is developed for computer utilization, and when more number of cold and hot streams are available in an industry, it is generally advisable to go for computer based algorithms, and that computer based algorithm is problem table algorithm, and we will see this in our subsequent lectures what is actually is a problem table algorithm. But at this time you should know that energy targeting can be done either using hot and cold composite curves or grand composite curve or problem table algorithm. The present lecture deals with the energy targeting using hot and cold composite curves. Let us explain this with an example. So, we take a 4 stream problem where 2 cold and 2 hot process streams are available. Their supply temperature, target temperature, their delta H values and heat capacity flow rates are given, and the delta T minimum considered for this case is 10 degree centigrade. You may ask a question that why 10 degree centigrade, why not different values? This delta T minimum is a ad hoc value which we have selected in this case for 10 degree centigrades. There are some thumb rules based on which we assume delta T minimum values to start with, but this delta T minimum value can be changed and we can find out the amount of hot utility and cold utility for different delta T minimum values. This is possible, and then we also design heat exchanger networks for different delta T minimum values and select a particular delta T minimum value which we will call delta T minimum optimum, at which the heat exchanger network cost is minimum, and then the whole network is being operated at that delta T minimum optimum value, because the heat transfer, the required heat transfer with that particular design operating at a particular delta T minimum optimum value will take minimum cost to transfer the heat. So, the first job is to take the hot streams and create a composite hot stream, and we have created that. The hot streams moves from 40 degree centigrade to 250 degree centigrade, the composite hot, and similarly we will also create a composite cold stream, and then after making this, that is composite hot streams and composite cold streams, we will bring them together and will find out what is the value of the hot utility and cold utility. So, this is the composite hot stream, it is brought here, then we go for composite cold streams, then we bring to the same graph here. So, we have put composite hot stream as well as composite cold stream, and the delta T minimum is here 10 degree centigrade, because in the problem we have assumed that the delta T minimum is 10 degree centigrade, and based on this we will find out the requirement of hot utility as well as cold utility. I have already told you that the amount of hot utility and cold utility is a function of delta T minimum. So, once I fix delta T minimum, I also fix the amount of hot utility and cold utility. So, this blue area shows the heat exchange area, and when I say heat exchange area, this is exchange between process stream to process stream. So, hot process stream are giving heat to the cold process stream in this area, and those area which are not covered here will be heated or will be cooled by external means or by external hot utility and cold utility, which are either steam or cooling water. So, in this problem, the external hot utility requirement is 7.5 kilowatt and the external cooling UT demand is 10, and internal heat exchange, that is Q recovery, is 51.5, and these values, that is 10, 51.5 and 7.5 are function of delta T minimum. So, when I say delta T minimum is equal to 10 degree, these three values are fixed, that is 10, 51.5 and 7.5. The overshoot of the hot composite represents the minimum amount of external cooling required. This is QC minimum is 10 megawatt, and the overshoot of the cold composite represents the minimum amount of external heating, that is QH minimum is 7.5 megawatt. The physical meaning is that this overshoot, which starts from here and goes to here, this is the hot stream overshoot, hot composite stream overshoot. This hot stream, composite hot stream, may have different number of hot streams. It clearly says that those hot streams which are here in the composite will require external cooling to come to this point. Similarly, here the cold streams, the composite cold streams which are here, that means there can be a number of different hot streams here, and these number of cold streams are here. So, this requires external heating to bring from this temperature to this temperature, which is equal to 7.5 megawatt. That means, if I pass 7.5 megawatts from here, then these streams can be heated from this point to this point. Similarly, this hot composite can be cooled from this point to this point if I use cold utility worth 10 megawatt. Now, let us see what is the effect of delta T minimum. We know that if we shift the cold composite curve in the horizontal direction, we can change the delta T minimum value, and if we change the delta T minimum value, the amount of cold utility will change, amount of hot utility will change, and Q recovery, which is the exchange, that is shown by this blue area, will be also change. That means, from this point to this point, this amount will also change. So, in this case, we have made a table for delta T minimum equal to 10. We have already seen that Q recovery is 51.5, QC minimum is 10 and QH minimum is 7.5, and total heat load, that means total heat transacted, which is a summation of these three quantities, is 69. So, my heat transfer area will be a function of Q total, because this much of heat has to be passed, and my delta T minimum, which is somewhere here, which is 10 degree centigrade, will give me these figures 51.5, 10 and 7.5, and total is 69. Now, if I shift this horizontally and make the delta T minimum is equal to 20 degree centigrade, then these figures will change. Now, I have QC minimum is 14, Q recovery is 47.5 and QH minimum is 11.5. that shows that if delta T minimum is increased, my hot and cold utility amount is increasing, but Q recovery, which is the exchange to a process exchange, is decreasing. So, here we see that for 20 degree centigrade of delta T minimum, Q recovery is 47.5, QC minimum 14, QH minimum 11.5 and total is 73. Now, you shift further. Here the delta T minimum is 30 and these figures again change. Now, my QC minimum is 18, Q recovery is 43.5 and QH minimum is 15.5 and the total Q is 77. Now, what I understand from this? There are two forces which are working here, and to analyze these two forces we use the formula which is Q is equal to U A delta T ln, which is written here. Now, for a fixed Q and for a fixed U, if delta T ln is increasing, A will decrease, this we know, and when we increase the delta T minimum value, basically we are increasing the delta T ln value. So, for a fixed Q, the area will decrease, and that is why we have seen that the fixed cost of a heat exchanger network decreases when we increase the delta T minimum value. But what we see here is a different story. What we see here, that when we are increasing delta T minimum, that means we are increasing the driving force for the heat transfer. The amount of total heat which needs to be transacted is also increasing. At delta T minimum equal to 10 degree centigrade, this was 69. At delta T minimum as 20 degree centigrade, this was 73. Delta T minimum at 30 degree centigrade, it was 77. So, this Q is also increasing. So, when delta T minimum is changing or increasing, the Q is also increasing. This is a conclusion we make from this. That means, Q never remains constant when we change delta T minimum. And if so happens, when delta T minimum is increasing, Q is also increasing, the benefit which we got by keeping the delta Q is equal to constant, that logic no more holds good, and hence the effect of increase in delta T minimum is not so prominent in this case as it has been when the Q remains constant. So, we take a second example where there are two hot streams and two cold streams and delta T minimum is 10 degree centigrade. So, we plot the composite hot, we plot the composite cold, and here the delta T minimum is 10 degree centigrade, the vertical distance between this point and this point, and we get here two pinch points, one is called hot pinch and another is called cold pinch. And many times students are confused when say pinch point, it appears to them that it is a single point, but it is not so. This will only happen when this cold curve, the cold composite curve touches the hot composite curve, then pinch point, this point will overlap over this and I will get a single point. But when there is a delta T minimum is specified, as in this case 10 degree centigrade, it tells that the temperature difference between this point and this point is 10 degree centigrade, and hence there is a hot pinch and there is a cold pinch, and the difference in temperature between hot pinch and cold pinch is 10 degree centigrade. Now, this is the area which shows the internal heat exchange, and this is 230 kilowatt in this, and here it shows Q hot minimum is 175 kilowatt. This is a hot external utility, and this shows 250 kilowatt is QC cold minimum. This is external cold utility. Now, I would like to say that the hot utility and cold utility which you calculate using this energy target are minimum requirement. The pinch analysis does not talk about the maximum amount of cold utility or hot utility demand. These are the minimum, you cannot go below this if energy conservation principles are to be sustained. So, it always gives you minimum amount, and that is why we write down Q hot minimum and Q cold minimum. So, this figures very clearly tells there are the salient features that 175 kilowatt of hot utility is required, 200 kilowatt of cold utility is required, and the heat exchange between process hot steam to the process cold steam is 230 kilowatt, and the hot pinch as at 90 degree centigrade and the cold pinch is at 80 degree centigrade, and all these values are for delta T minimum equal to 10 degree centigrade. If I change the delta T minimum value, these values will change, that means 175, 250 and 230, and the hot pinch and cold pinch temperature will change. Now, when we calculate the minimum amount of external utility, this is based on vertical heat transfer. That means, the requirement, this is the hot composite curve and this is the cold composite curve. Say this area is filled up vertical lines, shows the amount of hot utility. So, the hot utility which is here passes it vertically to hit the cold streams available from this point to this point. This is a composite cold composite curve. Similarly, the cold composite curve ends here, and this is the protruded portion of the hot composite curve. So, this hot composite curve will vertically pass heat to the cold utility which is here. So, in this case we consider that the utilities are transferring it vertically, as well as the process to process heat transfer is also vertically taking place. Now, if we take that problem and find out what is the amount of cold utility, what is the amount of hot utility and what is the amount of internal exchange and what is the total amount, then we come to this figures. That is, if delta T minimum is 5, the cold utility requirement is 225, hot utility requirement is 150, internal heat exchange is 255 and total heat exchange is 630. If we take it to be 15 degree, then the same values, that is cold utility demand rises from 225 to 275, hot utility amount rises from 150 to 200, and the internal exchange decreases from 255 to 205, and the total increases from the 630 to 680. So, here we see that when I am increasing the delta T minimum, the cold utility demand is increasing, the hot utility demand is increasing, and the internal exchange is decreasing, and the overall heat exchange is increasing. That means, if delta T minimum is increased, then utility cost will increase, whether it is hot utility or it is cold utility, and internal heat exchange will decrease. This is not a good symptom, because I have to spend more on utilities cost, and the total heat exchange is also increasing. That means, if I am increasing the delta T minimum, a part of it will be nullified by the increase in total heat exchange. So, the benefit which I get due to the higher driving force is not that much when Q remains constant. So, what conclusion I draw from this is internal heat exchange decreases and the value of cold and hot utility as well as the value of total heat exchange increases as delta T minimum increases. Due to the increase in the value of external cold and hot utilities, the operating cost of the hen increases. Further, the decrease in internal heat exchange decreases the scope of energy conservation in the process. So, basically if I want energy conservation in the process, I have to maximize the internal heat exchange, which is not taking place when delta T minimum is increasing. An increase in the value of delta T minimum increases the value of delta T available in all the heat exchanger in the hen, because when I am increasing the delta T minimum, all the delta T values of the heat exchangers are on increasing. Basically, in a heat exchanger there are two delta T values, one in the input side, other in the output side. If I call them delta T 1 and delta T 2, then when I increase delta T minimum, this delta T 1 and delta T 2 both increase, and thus the fixed cost decreases, because now I am providing more value of delta T minimum and hence area decreases. But however, as the total heat exchange amount is increasing, it will offset. However, this is offset by the increase in total amount of heat exchange. Now, we will derive some principles of pinch. Now, in the pinch, we have seen that in the pinch there is no heat transfer takes place, and hence the pinch point divides the problem into two parts, and thus I can separate the complete problem into two parts from the point of pinch. Now, the upper part is called above pinch area and the lower part is called the below pinch area. In the above pinch area, external hot utility is required, and in the below pinch area, external cold utility is required. The section above the pinch works as a heat sink, because it accepts heat from the external heat sources, whereas the below pinch area rejects heat to the atmosphere, and hence it is a heat source. That means, the below pinch area is always ready to provide heat to the outside world, whereas the upper part of the pinch area is always ready to accept heat from the outside world, and that is why the upper pinch area is heat sink and the below pinch area is a heat source. Both the areas, that the upper pinch area and the lower pinch area, are under heat balance and no heat flows through the pinch section. That upper pinch area, the hot streams along with the external hot utility will transfer the heat to the cold streams, and they are in thermal balance. That means, whatever heat required for the cold stream to heat up from the pinch temperature to this temperature up to this level is fully satisfied by the composite hot here and the external hot utility. Similarly, whatever heat is available with this composite hot is given to the composite cold as well as to external cold utility. So, this is also in heat balance and this is also in heat balance, and no heat flows from here to here, that means across the pinch. This is only true if we consider vertical heat transfer in the whole section of the heat exchange process. Now, let us see what happens if we put some additional amount of heat equal to delta over and above Q hot minimum, then it is transferred to the above pinch section. The total external heat given to this section now becomes Q head hot minimum plus delta. That means, if I pass on a delta amount of heat to this area, then my hot utility amount becomes del Q h minimum plus delta. Now, when I add more heat to this, it is in thermal balance, then this amount of heat delta will pass through this pinch and will go to this area. Now, here the heat available with the composite hot is in balance with the cold composite cold and external cold utility. So, when this extra heat comes here, it will increase the external cold utility amount. So, the cold utility amount will now become Q c minimum plus delta. So, in this balanced pinch, if I am adding extra heat, then it goes through the whole process and lands up into increasing the cold utility amount. So, thus adding more heat above the pinch section is not fruitful, because it is not required, and if I am forcefully adding the heat, then what will happen? Addition of amount of heat required additional heat transfer area, hence cost increases due to increase in total area of the heat exchange. When I am adding this delta amount of heat, I cannot add as it is, I have to provide heat transfer area for this addition. So, the heat transfer area required for this above pinch section will increase, as well as the heat hot utility amount will also increase. So, the hot utility increase in hot utility amount will increase the operating cost, and increase in the area to transfer this delta amount of heat will increase the fixed cost of above the pinch section. Similarly, here also it is increasing the cold utility amount of cold utility by delta amount. So, the operating cost will increase for this, and also it will increase the area. because I have to provide more area for the coolers to transfer this delta amount of heat. So, external hot utility cost, which is also proportional to delta, increases. The cold utility cost increases proportional to delta, as well as the cost of heat transfer area also increases proportional to delta. Now, if I am adding a delta value here, so it goes through this and ends up here. Now, let us see that if I add a cold utility at the above pinch area and I add a hot utility into the below pinch area, then what happens? If the extra cold utility of amount delta is used in the above pinch area, which is under heat balance, it will cool the hot stream or hot utility by delta amount and will disturb the heat balance. Now, if I add a cold utility amount delta here, then what will happen? I have to increase the hot utility by delta amount to neutralize this cold utility. So, my hot utility amount is increasing. To bring it to the heat balance, extra hot utility of amount delta has to be added to Q hot minimum, and thus the total hot utility requirement to bring the section to the heat balance will now be Q hot minimum plus delta. Now, what this will do? This will increase the operating cost involved in the above the pinch area. This is first thing. The second thing is that to transfer this cold utility delta, I have to provide area and the cost of the cold utility, plus to transfer this delta amount which is added to the hot utility. That means, now my hot utility amount has increased by delta. So, the operating cost has increased, plus to transfer this delta amount of hot utility, I have to provide again area. So, this will increase the total hot utility cost as well as fixed cost of the heat exchanger, which will now transfer Q hot minimum plus delta heat in place of Q hot minimum. Now, in the below, as below the pinch section is under heat balance, the cold utility requirement will be Q cold minimum. So, below pinch the cold utility requirement is QC minimum, that is Q cold minimum. It will not increase, but the total cold utility will increase because you have added delta utility at the top. Similarly, if I am adding a hot utility to the below pinch area, then obviously overall hot utility demand increases, and then to nullify this hot utility of delta amount, I have to increase my cold utility amount proportionately. So, my cold utility amount is now Q cold minimum plus delta. So, cold utility amount has increased and hot total, if I see the total picture, then hot utility amount has also increased in this case, and the area required to transfer these utilities will also increase. However, the above pinch section, if I see, which is under heat balance already, will only require external heating of Q hot minimum. The overall hot utility will increase, but if I only see the above the pinch area, the hot utility amount will not increase for the over problem wherever, whereas it will increase. So, from this we conclude something. What is the conclusion? Do not transfer heat across the pinch as the penalty is twice, because if I transfer heat through the pinch, then I pay in terms of area, I pay in terms of utility. My hot utility increases, my cold utility increases, and the area required to transfer the extra amount of hot utility and cold utility also increases, and that is why the penalty is twice. So, in the design I will see that whatever utility is required, I will pass only that much of utility and will not go for extra utilities. If we see the designs, old designs, we will see that if you analyze the old designs which are there in the industry, you will find that in many cases extra heat is being passed than required, and that is why the cost of the heat exchanger network, that is operating cost as well as the fixed cost of the heat exchanger network is higher. So, by correcting this, we can bring down the cost of operation of the heat exchanger network. So, it gives a scope to analyze already available heat exchanger networks and to decrease their operating cost. In this way, pinch saves a lot when it is applied to a existing industry. The second point is, do not use cold utility in the above pinch section. We have seen that if we use cold utility in the above pinch section, the hot utility demand increases, and then the cold utility demand, overall cold utility demand also increases, and then the area required for this also increases by the amount of increase in cold and hot utility. The third point is that do not use hot utility in below pinch. This also can be argued out in the same manner. When we use hot utility below the pinch, we increase the cold utility amount and hot utility amount also for the total problem, and also more area is required to pass this extra amount of hot and cold utility. So, this increases unnecessarily the cost of the heat exchanger network. So, when we will design, we will keep this in mind that we will not pass heat across the pinch, we will not use any cold utility in the above pinch section, and we will not use any hot utility in the below pinch section. And if in some existing designs these are found, these faults are found, we can correct them and we can decrease the cost of heat exchanger network as well as the operating cost of the heat exchanger network. These faults are generally committed in old designs which were carried out without using pinch analysis, and hence provide opportunity to correct these designs and save fixed as well as utility cost. Thank you.